When a severe storm rolls over a city, it feels like a purely physical, uncontrollable force of nature. We rely entirely on knowing exactly where that force will go to protect our power grids, our crops, and our daily commutes. Yet, despite spending billions of dollars on orbital sensors and supercomputers, our ability to tell you if it will rain exactly 16 days from now is practically zero. We haven't hit this wall because our satellites lack resolution or because our processors are too slow. Meteorology is an ongoing, desperate attempt to solve a highly complex, continuously changing math problem. The sun bombards the equator with an extreme surplus of shortwave radiation, leaving the poles in a deep deficit. To resolve this severe temperature gradient, the Earth acts as a heat engine, pushing thermal energy outward toward the freezing poles. It uses the lowest layer of our atmosphere, the troposphere, as a medium. Because the air here acts roughly as an ideal gas, it obeys strict thermodynamic rules. As the surface heats up, the air directly above it expands. Its density drops, forcing it to rise and eventually cool, a physical mechanism called an adiabatic process. As that rising air cools, its water vapor condenses into liquid. This phase change releases latent heat, dumping sudden, explosive energy into the air, the exact fuel required to turn a cloudy afternoon into a severe thunderstorm. These thermodynamic reactions form a massive, invisible vertical engine driving every weather event on the planet. If the Earth stood completely still, all that heated air would flow in an orderly, straight line from the equator to the poles. But looking at this rotating model, we see how the Coriolis effect violently bends those moving air currents, curving them to the right in the north and to the left in the south. Tracking this wildly twisting fluid requires the Navier-Stokes equations. These formulas describe how chaotic twisting organizes into a massive planetary macrostructure, stacking the atmosphere into three enormous loops of air: the Hadley, Ferrel, and polar cells. The boundaries where these gigantic cells collide generate extreme friction and sharp temperature gradients. This friction produces high-altitude jet streams that rip across the sky at over 300 kilometers per hour, steering storm systems across entire continents. Everything we call weather is the byproduct of this giant churning fluid machine, desperately trying to balance its temperature while spinning at supersonic speeds. To predict what this fluid machine will do tomorrow, numerical weather prediction gathers the current state of the atmosphere and plugs it straight into those exact fluid and thermodynamic equations. Historically, gathering those starting numbers was a grueling physical chore. Meteorologists released radiosondes attached to weather balloons to physically capture precise temperature, density, and pressure readings miles above the ground. They then had to organize this raw, localized data by hand, plotting symbols onto analog wall maps to trace large-scale synoptic patterns. Today, those scattered physical readings are replaced by millions of continuous data points, fed directly into supercomputers specifically built to crush the Navier-Stokes equations. The daily forecast on your phone is the final output of millions of complex math equations solved simultaneously by machines. In the 1960s, a mathematician and meteorologist named Edward Lorenz discovered a fatal catch buried deep inside those fluid equations. Because it is physically impossible to measure the exact temperature and location of every single air molecule on Earth, our starting data always contains microscopic imperfections. We always round off a decimal point somewhere. This graph tracks a theoretical weather trajectory. Lorenz proved that in a highly nonlinear fluid system like our atmosphere, microscopic rounding errors compound exponentially. By day 15 of a calculation, the tiny errors entirely consume the data, and the mathematical model violently shatters. This rapid, catastrophic mathematical divergence gave birth to the famous concept we now call the butterfly effect. That 15-day limit is an absolute law of nature. Our ability to accurately track a hurricane's path 5 days out is a towering triumph of human ingenuity against the raw bounds of chaos.